Hi everyone. Today I will be talking about some basic ideas of tensor analysis. Actually, what are tensors? Tensors are nothing but the generalization of scalars and vectors. We all know that scalars and vectors are mathematical tools to represent the physical formulation of laws. In a similar fashion, tensors are also necessary in the mathematical formulation of physical laws. For example, in many physical problems, such as the description of elastic, optical, electrical, magnetic properties of anisotropic materials, a tensor is highly necessary. Let me quote an example for this. For example, when we learn the physical properties of anisotropic solids, the scalar and vector notations are not sufficient to express the relations between quantities involved in the physical process. This shows that anisotropic nature demands the mathematical tool tensor. Let me substantiate that point clearly. You look at this, or you take a ball of mass m, place it on a table, and the ball is kept in an isotropic medium. Isotropic medium means showing the same property in all directions. Suppose I give a push to the ball with a force F. Everybody knows that the ball acquires an acceleration along the same direction. According to Newton's second law, we have F is equal to ma. In this particular problem, because the ball is kept in an isotropic medium, correct? And simply because of that, the direction of the force and the direction of acceleration are one and the same. So I can very well write m is equal to F by A. Correct? Since the direction of F and the direction of A are the same, they cut off. So what remains is a scalar quantity, which is the mass. Let me repeat once again. Since the ball is kept in an isotropic medium, if you apply a force in particular direction, the ball acquires an acceleration in the same direction. So F and A will have the same direction. So these two directions get cancelled. So what remains is a scalar. So on the right hand side, there is a scalar we call mass. So for the time being, I'm going to redefine what is a scalar quantity. At the plus 2 level, we define a scalar quantity is having only magnitude. Here also, here the directions get a cut off, scalar quantity. Now, here I am going to redefine a scalar quantity. What is a scalar quantity? A scalar quantity is a coupling constant between these two vectors acting in the same direction. Correct? So scalar is a coupling constant, correct, between two vectors in the same direction. Suppose F and A are having different directions, so the nature of M will be different. Here the tool tensor emerges. Let me put it in another way. Suppose I keep a ball of mass M in an anisotropic liquid, partially immersed. I apply a force, and the acceleration will not be in the same direction because the medium surrounding the ball is anisotropic. So the acceleration will be different. In that case, how can we couple the force acting in one direction, acceleration acting in different direction, or coupled? Then we got a very specific example for that. Suppose F is equal to some 3I plus 2J plus 4K. It's only an example. And the acceleration of the ball in the liquid is 2I plus 6J plus 8K. Correct? By using Newton's second law, F is equal to ma, I want to couple A and F. How it is possible? Look at this carefully. F is equal to, remember that here the medium is anisotropic. Correct? Now look at this. The direction of F is not the same as the direction of A. Entirely different. So how can we couple A and F? Correct? To simplify this, F is equal to ma. I am writing F as the three components, 3 along the I direction, 2 along the J direction, 4 along the K direction, which is equal to some mass M into A. A means 2, next one is 6, 8. This can be coupled only if M is a 3 by 3 matrix. The reason is I wrote F as a column matrix and A as a column matrix. So M must be a 3 by 3 matrix. The reason is obvious. It's a column matrix 3 by 1. 3 rows and 1 column, which is equal to, is also 3 rows and 1 column. And this will be satisfied provided this must be a 3 by 3 matrix. Correct? This will cut off and we will get 3 by 1. Here also 3 by 1. So mass is an entity having a 3 by 3 matrix containing 9 elements. And these 9 components are called tensors. Now, let me do it in a different way. Here F is equal to 3, 2, 4, 3 by 3, which is 2, 6, 8. Oh, I can very well fill it. The matrix 3 by 3 matrix, I can very well fill it. That is, this is an example. Here 3 we should get 3 by 2 into 2 plus 0 into 6 plus 0 into 8, obviously 3. Next one, here you should get 2, 0 into 2 plus 1 by 3 into 6 plus 0 into 8. Correct? You get 2. 0 into 2 plus 0 into 6 plus 1 by 2 into 8. So the scalar mass m turns out to be a non-component entity called tensor. Correct? This shows that anisotropic nature of the material demands one more mathematical tool called tensors. Now I am going to generalize this thing. Correct? Look at this. This is the x component of the force Fx. This is, I call it as one of the components of the mass. I call it as mxx into ax plus this I call it as mxy into this fellow I call it as ay, or there should be ay plus mxz, this one msz. This is a generalization. Similarly, you can write down all other terms. That is, Fy is equal to myx ax plus myy ay plus myz sz. Similarly, fz is equal to mxz ax plus mxy ay plus sorry, I made a mistake. Fz is equal to mzx ax. This is mzy, and the last one is mzz sh. This is a generalization. Now, in the former case, when f and a are acting in the same direction, m turns out to be a scalar having only one component, which is a scalar. Now, in this particular case, when f and a are in the different direction, m turns out to be a non-component entity called a tensor. Correct? Now, I can symbolically write down this force acceleration relation as see the way in which I am developing this symbolic nature. I am attaching a symbol to this. You can very well think of, since f and a are acting in the different direction, where I is equal to x, y, z, and j is also equal to x, y, z. Correct? Now, I already told you m is the coupling constant between fi and aj. So, m should be rewritten as, am I correct? M is a coupling constant between fi and aj, or I can say m is ij. It has to be summed over j is equal to x to z. When you expand this, we get the old relation. So, this is a non-component entity called a tensor. This is the reason I already told you. Anisotropic nature demands the mathematical tool tensor. Correct? Now, let me quote another beautiful example. How a tensor arises in certain other respects. For example, you may have familiar with this relation. J is equal to sigma e. J is called the current density E is called the electric field and sigma is called the conductivity. Now, if you take a isotropic material, be very careful. If you take an isotropic material and an electric field is applied to it, electric field is applied to it. Since it is isotropic, the current density is also along the same direction. So the direction of J and direction of E are along the same direction since the conductor is isotropic. Correct? Since these two are along the same direction, I can very well write sigma is equal to J by E. And these two directions get cut off. We get a scalar quantity. So in that context, sigma is a scalar quantity, or the conductivity sigma is a scalar quantity, provided J and E are acting along the same direction. This happens only when the conductor is a isotropic material. Correct? But we know that almost all conductors are anisotropic in nature. Correct? In that context, what will happen? Correct? In that context, J and E will be in different directions. J and E will be in different directions because the conductor is anisotropic. In that context, I already shown that sigma will be an entity called a tensor. Here also we have non-components. Correct? So symbolically this can be written as Ji is a, so sigma is a coupling constant between I and J. So I have to attach two indices here, summing over J. J runs from X, Y, Z. Correct? So this is another example. Correct? Wherever you want to couple between two vectors in different directions, definitely the tensor will come into play. And this tensor nature is actually due to the presence of anisotropic nature of the material. Let me go to another example. Suppose I have a very famous example at the +2 level. J is L is equal to I omega. L is the angular momentum, I is the moment of inertia, then omega is the angular velocity. Correct? If L and omega are acting along the same direction, obviously we can say I is a scalar. I is a scalar. So moment of inertia is a scalar quantity. Correct? This is not always happening so, because this can happen only when L and omega are acting along the same direction. For example, you take a sphere and revolving radius, and the angular momentum direction is obviously along the axis, or omega is also along the axis. So L and omega are acting along the same direction, so I tensor to be a scalar. Suppose the ball is inclined and a spherical ball. Suppose you take an inclined axis and rotate it. Obviously, L and omega will be different. So in general, L and omega will be different. In that context, I tensor to be a tensor having 9 components. So in tensor language, this can be written as L is I omega, right on the way in which I am writing tensors. I, J, because both are having different directions. So I already told you this fellow is a coupling constant between I and J. So I had to add I, J. And it has to be summed over J. J can be X component, Y component, and Z component. Now, there are several examples for this. You take another example for this. This example is a very familiar example where P is called the polarizability and E is the electric field. So, if your medium is isotropic, P and E will have the same direction. Same direction means same direction will cut off. So, what remains is a scalar. So, the susceptibility or electric susceptibility is a scalar. Correct? But almost all materials are anisotropic in nature. So, these two have different directions. In that context, this turns out to be a non-component entity called tensor. Correct? So, in the tensor language, this can be written as like this: I, J, where K is the coupling constant, I, J, summing over J. J can be X, Y, and Z. In this case, susceptibility becomes a non-component entity called tensor. Correct? So, now we can differentiate between a scalar, vector, and a tensor. A scalar is a quantity having only magnitude in all dimensions. It's a very important thing. A scalar is a quantity having only magnitude in all dimensions. In 1 dimension, 2 dimension, 3 dimension. If it is a scalar, it has only one component. But you take a vector. In 1 dimension, it has one component. If you are dealing with a vector in 2 dimensions, the number of components is 2. If you are dealing with the 3-dimensional space, it will have 3 components. If you are dealing with a 4-dimensional Minkowski space, 4 dimensions. If you are dealing with an n-dimensional space, it will have n components. So, the peculiarity of vector is that the number of components is equal to the number of dimensionality. Here, only one magnitude in all dimensions. But what about in tensors? We could see that we dealt with several examples in 3 dimensions. In 3 dimensions, this coupling constant has 9 components. Correct? So, what is a tensor? A tensor is a quantity having large number of components than the dimensionality. We dealt with so many examples in 3 dimensions. In 3 dimensions, we could see that mass has 9 components. And the conductivity has 9 components. The moment of inertia has 9 components. All are in 3 dimensions. This is actually the difference between a scalar and a vector and a tensor. A scalar is a quantity having only one component in all directions. Vector is a quantity having same number of components of the dimension. And tensor always having large number of components than the number of dimensionality. So, now we could see that anisotropic nature demands one more mathematical tool called tensors. Another very important point to be noted is that I already told you in the first example, a physical MA, if Fn AR or F is equal to F by M, F by A, if both are having same direction, M is a scalar because directions get cancelled. But if A and A are different directions, this turns out to be a non-component entity called tensor. In your lower classes, you might have studied that a vector cannot be divided by a vector. That is not actually true. When we come to higher levels, we can see that a vector can be divided by a vector. Look at this. A vector can be divided by a vector. Both are having same direction, the result will be a scalar. If these two are a vector divided by another vector, but both are having different directions, you will get a tensor. So a vector can be divided by a vector. The result will be a tensor if both are having different directions. The result will be a scalar if both are having same directions. Correct. Now you may ask, sir, in dealing with the anisotropic system, M turns out to be a tensor. Correct. So what is actually the mass of the ball? I told you an example in the earlier case. M turns out to be a non-component entity called tensor. And what about the mass? Mass is split into 9 components. Correct? Everybody knows that actually the non-component entity matrix, non-component mass is written as a matrix. Correct? And every matrix is associated with a value called determinant. If you take the determinant of that matrix, automatically that gives you the mass of the ball that we taken. It's a very crucial thing. Let me recall our example once again. 3, 2, 4 are the components of the force. 2, 6, 8 are the components of the acceleration. And these are the components of the mass. Alright. You are familiar with mass as a single entity. Here, the mass has become a non-component entity. Is there a relation between them? Definitely. Correct? Actually, I wrote this as a matrix form. And we know that a single value is associated with a matrix called determinant. If you go for the determinant of this fellow, you will get a one value. That is actually the mass of the ball. The determinant of this matrix is very simple one, that is 3 by 2 into 1 by 3 into 1 by 2. Correct? So answer is 1 by 4. 1 by 4 kilogram or 250 gram. So nothing happens actually. A single entity 250 gram is split into 9 components. That is actually what happens. Sometimes you may ask where this will be useful. I already told you, when we are dealing with an anisotropic system, this is highly necessary. Another example. Suppose an electron is moving through a sodium chloride crystal. Sodium chloride crystal. Sodium chloride crystal is highly anisotropic. So the mass of the electron will be a non-component entity. Then only you can predict acceleration by knowing the force. The force experienced by the electron is coming from the potential barrier of the crystal. Correct? So force is known. Correct? Force is known. Suppose I want to predict acceleration. In that context, M becomes, then F and A will be obviously different, because sodium chloride crystal is completely anisotropic. So to predict A knowing F, M automatically turns out to be a tensor, a non-component entity. If you take the determinant of this 3 by 3 matrix, you will get the mass of the electron, which is equal to 9.1 into 10 raised to minus 31 kilogram. That is all. Correct? Actually, this is the essence of emergence of tensors. This is one of the reasons why tensors are necessary. For one more reason, tensor analysis is necessary. We all know that the fundamental laws of physics should possess the same form in all coordinate systems. This steady or well accepted fact is known as the invariant formulation of physical laws. Correct? But here there is a problem. When we deal with the Euclidean space, we all know that physical laws are invariant under Galilean transformation. When we deal with the four-dimensional Minkowski space, I mean relativity, physical laws are invariant under Lorentz transformation. When we deal with the Hamilton's equations of motion, we know that they are invariant under canonical transformations, and so on and so forth. But if you express our physical relations in tensor form, it will be invariant under all types of transformations. So the invariant nature of the physical laws are embodied in tensor analysis. Correct? If we express the physical laws in terms of tensors, it will be invariant under all coordinate transformations. And this is the second reason we require tensor analysis. I told you, if we express physical laws in terms of tensors, they are invariant under all coordinate transformations. You may ask why. This is because tensor is an entity which is independent of the coordinate system to which its components are referred. By concluding, we can say tensor answers three questions. 1. Are all physical laws expressible in terms of scalars and vectors? You know the answer now. No. Tensor is also necessary. The second one is that how should a physical law be rewritten if a wider class of transformation is involved? If a wider class of transformation involved means the isotropic nature and as well as anisotropic nature. Anisotropic nature is the wider class of transformation. And the third question is, with respect to which transformation does a physical law is invariant? Actually, tensor answers these three major questions. Actually, the systematic study of tensor analysis was begun by Italian mathematician Ricci. Later on, it was developed by Lewis Vita, a student of Ricci. But the tensor analysis became more popular when Albert Einstein used this as a tool for developing general theory of relativity. Nowadays, everybody knows that in all branches of theoretical physics, tensor analysis is highly necessary. For example, while dealing higher level classical physics, electromagnetic theory, quantum mechanics, quantum chromodynamics, elastic properties In all branches of theoretical physics, this tool is highly inevitable. Once it was thought that scalars and vectors form a complete mathematical tool to represent physical laws. Later on, it was realized that these two tools are not sufficient. One more tool is required called tensors. Let me quote an example for this. In the realm of nuclear physics, everybody knows that spin zero particles are represented by scalars. Spin zero particles like pions, alpha particles, etc. Then what about the spin one particles? The spin one particles like photons, phonons, magnons, protons, etc. are spin one particles. And they could be represented by vectors. Correct? And the spinors, the fermions could be represented by spinors. Then what about the graviton? The graviton would be represented only by tensors. So tensor is highly necessary in higher level physics. After developing tensors, physics people developed two more mathematical tools. One is called differential forms. Other one is called NPTF. NPTF means Newman-Penrose-Tetrad formalism. So, at present, physics people are familiar with scalars, vectors, tensors, differential forms, and Newman-Penrose-Tetrad formalism. We pass on to the second part of tensor analysis. I just introduced how does tensor emerge, or what is the necessity of tensors. Actually, to learn tensor analysis in depth, we require three basic things, or two basic mathematical tools. One, Einstein's summation convention. Two, the Demian real indices. And the second one is the Chronicle Delta and its properties. And third one, the Lewis-Witta symbol and its properties. After learning these three simple mathematical tools, we can directly get on to tensor analysis. First of all, let me explain what is meant by Einstein's summation convention. This is actually some sort of simplification. Earlier, I wrote like this: Fi is equal to sum over j m I j a j. J runs from 1 to 3. 1 stands for x, 2 stands for y, and 3 stands for z. Only for simplification, I changed my notation. Instead of x, y, z, I am writing 1, 2, 3. Right? After some time, I will pass over 1 to 3 to 1 to n. Right. Now, let me explain what is meant by Einstein's summation convention. In this term, you can see that j is repeating and it is summed over j. Correct. So, what Einstein did is, both these symbols are not necessary, he quotes. Whenever an index is repeated in a term and the summation of that index or the range or the dimensionality is implied. Correct? If that is implied, we did not keep the summation there. Whenever an index is repeated, it goes without saying that summation is over j. So, I am going to remove this. And the removal of the summation sign is called Einstein's summation convention. Now, till the end of the topic, I will use this convention. Whenever an index is repeated, it goes without saying that summation is over that index or the range. Range could be anything. If we are dealing with 2 dimension, j runs from 1 to 2. If we are dealing with 3 dimension, 1 to 3. If we are dealing with 4 dimension, j runs from 1 to 4. If we are dealing with n dimension, j runs from 1 to 4. So the dropping of the summation or the domain is called Einstein's summation convention. Another example I quoted was ji is equal to summation over j sigma ij ej. Here j is repeated, so you need not write the summation again, but summation is there. Yeah. This is called Einstein's summation convention. If any index is repeated in a term, you need not write summation there. It implies, automatically implies, summation is there. Now, the repeated index j here is called demi-index. Repeated index is called demi-index. Demi in the sense that you can change the index j at your will. For example, I can very well write, instead of j, I can very well write fi is equal to m I k a k. This is the meaning of demi. Or you can write fi is equal to m I l a l. This is called demi-index. Demi-index can be replaced at your will. Any letter can be used. And what about the real index? If any physical relation, if an index occurs only once, it is called a real index. Right? For example, let me write an example for this. In this particular example, I is repeating here. So I is demi. So actually, you should remember that there is a summation here, summation over j. But in this term, alpha is not repeating. Alpha occurs only once. So alpha is called a free index. Here on the left hand side, alpha occurs only once. So alpha is called free index. But the main difference between the free index and the demi index is that demi index can be changed at your will. I already told you. But the free index should not be changed. The free index should not be changed. For example, y is equal to ai xi. Obviously, I is demi, and there is a summation here. Remember that always there is a summation there. So I can as well write this as aj xj, or I can write y is equal to ak x. This is the reason why it is called a demi. Correct? You can change that with any other index. But if it is a free index, that cannot be changed. This can be written as, this is a free index, so that index should not be changed. Dx bar alpha is equal to dou x bar alpha into dou xj dxj. Since it is demi, I can change. Since it is free, this is free and this is free, it should not be changed. Actually, this is the meaning. So, you may ask, sir, what is the domain of this summation? Here, there is a hidden summation over I. Correct? That depends upon the dimensionality that you are playing with. If you are dealing with the 2 dimension, I runs from 1 to 2. If you are dealing with the Mingosi space, 4-dimensional space, then I runs from 1 to 4. If you are dealing with the n dimension, I runs from 1 to 4. This is a very effective mathematical tool to simplify the study of tensor analysis. Another mathematical tool that we should be familiar is the Chronicle Delta symbol. What is actually the Chronicle Delta symbol? Let me explain this. I dot j. I dot j. We know that I dot j is equal to mod I mod j into cos theta, where theta is the angle between I and j. Suppose I is equal to j. I is equal to j means I is equal to j. So mod I cosine of the angle between I and j. Here theta is the angle between I and I. The angle between I and I is 0. So cos 0. So mod I is equal to 1. Mod I is 1. Cos 0 is 1. So this is equal to 1. So I can very well write I dot j is equal to 1.
I don't see.
What? If I is equal to j. I is equal to j. If I is not equal to j, if I is not equal to j, I is not equal to j, means I and j are perpendicular. Theta is 90. So I dot j is 0 if I is not equal to j. This is actually symbolized by Chronicle as delta ij. Correct? I dot j is symbolized by Chronicle as delta ij for simplicity. This is called the Chronicle Delta. So the definition of Chronicle Delta, delta ij is nothing but I dot j. So delta ij is equal to 1 if I and j coincides. If I is not equal to j, I and j doesn't coincide, equal to 0. So this is the basic definition of Chronicle Delta. Not only that, this Chronicle Delta exhibits some properties. Now we will look at the properties. Properties of Chronicle Delta. The very interesting property before the property Chronicle Delta, I should say one more thing. That is, delta ij is equal to 1 for I is equal to j, equal to 0 for I is not equal to. I can take three values, the x-axis, y-axis, z-axis. J can also take x-axis, y-axis, z-axis. Suppose I collect all delta ij's in three-dimensional space. Suppose I collect all delta ij's in a three-dimensional space, so that collectively you will have 9 components. Automatically, it turns out to be a tensor. Individually speaking, delta ij is a scalar, either 1 or 0. Suppose I'm connecting all the delta ij's, all possible delta ij's from a three-dimensional space. Correct? Then it will have 9 components. For example, delta xx, 1. Delta xy, delta xx, I is equal to x, j is equal to x. Next one is delta xy. Third one is delta xz. Fourth one is delta yx, delta yy, delta yz, delta zx, delta zy, delta zz. So, collecting all the delta ij's from three-dimensional space, collectively we have 9 components. So, it turns out to be a tensor by set area. Right? So, delta ij is a single entity. Correct? Delta ij is 1 or equal to 0. But if you are collecting all the delta ij's from a three-dimensional space, it is a non-component entity called tensor. Or this can also be written as delta xx, I is equal to j, 1. Delta xy, x and y are different, 0. X and z are different, 0. So similarly, these are the 9 components of Chronicle Delta in three-dimensional space. This can be extended to any level, 4-dimensional space, 5-dimensional space, etc. Right? Another important property exhibited by Chronicle Delta is, you consider a coordinate system, a three-dimensional coordinate system. For example, I am considering this as x superscript I, indicating x1, x2, x3, 3 coordinates. Actually, this is x coordinate, and this is y coordinate, and this is z coordinate. So, the 3 coordinates are symbolically represented by xi, not x power I, xi. I is equal to 1, 2, 3. And we all know that x1, x2, x3 are mutually independent. Mutually independent means xi, dxi, by dxj, derivative xi with respect to derivative xj. Right? This is equal to 1 when I is equal to j. When I and j are different, you take any value, dx1 by dx2, they are perpendicular. Right? So, this is equal to 0. This is the same property exhibited by Chronicle Delta. So, delta ij can be written as dxi by dxj. Right? So, this is in general for any coordinate system, any orthogonal coordinate system. Delta ij is equal to dxi by dxj. Now, you take some other coordinate system. I am taking the second coordinate system as x bar alpha, bar representing another coordinate system. Alpha is equal to 1, 2, 3. Correct? Or x bar 1, x bar 2, x bar 3. In a similar fashion, I can write dx bar alpha by dx bar beta is equal to 1 provided alpha is equal to beta. If alpha and beta are different, they are always perpendicular. So this is equal to 0, exhibiting the same property of the chronicle delta. So this can be symbolized as, so delta ij is equal to dx I by dxj. Delta alpha beta is equal to dx bar alpha by dx bar beta. Usually Si is a coordinate system, say Cartesian coordinates. X bar alpha is some other coordinate system, say spherical polar coordinates. Correct. Usually we go from Cartesian to spherical polar or spherical polar to Cartesian. Or I can very well say x bar alpha is a function of xi. Alright, x bar alpha is a function of xi. So x bar alpha is a function of xi. Now I can correlate these two. That is, look at this case here. That is dxi by dxj is equal to delta ij. You take some other coordinate system, ds bar alpha by dx bar beta is equal to delta alpha beta. We simply put a bar over x just to differentiate or just to show that this is a separate coordinate system other than this one. There is no meaning at all. Now we go from a Cartesian coordinate system to spherical polar coordinate system or vice versa. In that context, I can very well write this as dx bar alpha by dx bar beta can be written as dou x bar alpha by dou xi into dou xi by dou x bar beta. You might be remembering the function of a function rule. Correct? We are very well careful about this. Here I is dummy and there must be a summation over I here. So this is a function of a function rule. We are very careful about that. So it's a very lengthy equation. I is a dummy here. So there is a summation over I. Correct. Now, using the symbolization symbol, correct, I can very well write this as delta alpha beta. This can be written as delta alpha I, delta alpha I. This is delta I beta. Correct. This can be extensively used. Correct. Now we can write down some other properties exhibited by Chronicle. For example, delta ij ai. This will survive only when I is equal to j. When I is equal to j, this becomes 1 and this value becomes I is equal to j. It's a very simple idea. Correct? Delta ij into I, because this will survive only when I is equal to j. When I is equal to j, this becomes 1. So ai goes to aj. So this is one relation. Another relation is very important. Delta ij is always equal to delta j. Because this is I dot j and this is j dot I. Everybody knows that I dot j is equal to j dot I because scalar product is correct. It can be written like this. So delta ij is equal to delta j. Now another important point is delta ij into delta jk is obviously delta ik. This I already proved. This will cut off. This I already proved. Another very important point is the value of delta I. The value of delta I can take 1, 2, 3. J can also take 1, 2, 3. So this value must be 3 in 3 dimensions. If I write like delta 1, 1, only one value is equal to 1. Or if I write delta 3, 3, delta 3, 3, obviously 1. But in general, delta Ia is equal to 3 in 3 dimensions. But the delta Ia is equal to 4 in 4 dimensions. Delta Ia is equal to n in n dimension. Correct? Because I can take 1, 2, 3. So delta 1, 1, 1. Correct? Let me explain that in detail. Delta Ii, this is repeating. So according to summation convention, this can be written as summation over I delta Ii. I runs from 1 to 3, expanding, which is equal to delta 1i plus delta 2i plus delta 3i. Now some more I, delta 1, 1 plus delta 1, 2 plus delta 1, 3. Expansion of this one. Now 2i, delta 2i can be written as delta 2, 1 plus delta 2, 2 plus delta 2, 3. And this fellow can be written as delta 3, 1 plus delta 3, 2 plus delta 3, 3. When I is not equal to j, Chronicle delta will vanish. So 0, 0, 0, 0, 0, 0. So only 3 terms will survive. Delta 1, 1. Everybody knows that it's 1. Answer is 1. Plus 1. Plus 1. So answer is 3. So the value of delta Ii in 3 dimension is 3. But in 4 dimension, delta Ii is 4. In n dimension, delta Ii is n. These are some of the properties exhibited by now. Let me quote a very simple application of Chronicle delta in the realm of tensors. You consider a vector A which has 3 components, A1, A2, A3. These are the components, vector components. In tensor language, this fellow can be rewritten as AII. Correct? Expanding, we get A is equal to AXI plus A1 1 cap plus A2 2 cap plus A3 3 cap. 1 means X, 2 means Y, 3 means J. So symbolically in tensor world, vector I is written as AI I cap. This is the tensor notation. This is the vector notation. Similarly, take another vector B. This is written as some Bj into J. Correct? Be very careful. I already told you Einstein summation convention. Here I is repeating. I is repeating. So there is a summation here. Correct? So it is a 3-time. A 3-time entity. Here J is repeating. So summation is there. So this is the 3-time entity. Correct? Now I want to find out what is A dot B. All know that in vector world, A dot B is equal to AX BX plus AY BY plus SZ BZ. Correct? In the terminology of tensor, how can we rewrite this? Look at this. This can be rewritten as A is AII tensor notation dot B tensor notation. AI are the components of the vector A. Bj are the components of the vector B. So these are numbers AI, Bj into I dot j. I dot j. But I dot j is delta ij. So AI Bj delta ij. Right? So A dot B is equal to, this is the tensor language and this is the vector language. AI Bj delta ij. But everybody knows that delta ij will survive only when I is equal to j. When I is not equal to j, this will 0. This will become 0. So when I is equal to j, this will survive. So A dot B is equal to, this will survive only when I is equal to j. I is equal to j means in that context this is 1. So this is AI Bi. So this is the difference between the two languages. In vector language, we usually write the dot product as A dot B. But in tensor language, there is no dot or there is no cross. Only AI Bi. Let me expand this. Correct? This is demi. Demi can be written as sum over I AI Bi. Correct? I runs from, we are dealing with the 3 dimension. So I runs from 1 to 3. Expanding that, I can very well write A1, B1 plus A2, B2 plus A3, B3. One is our X, so AX, BX. 2 is our Y, AY, BY. 3 is our K, AK, BK. This is the difference between the two languages. Correct? This is the language in the vector world and this is the language in the tensor world. Suppose we are dealing with n dimension, which is more elegant. This is more elegant because when we deal with n dimension, simply what we have to do is make it I runs from 1 to n. That is all. Suppose we are dealing with the Minkowski space, I runs from 1 to 4. That is the elegance of using tensors. Correct? I have shown this just to understand the application of the Chronicle Delta. Now I had told you we have to go through one more mathematical tool called Levi-Civita symbol. This is another very important tool to learn tensor analysis in depth. You might have heard of A dot B cross C. A dot B cross C. All know that this is nothing but the volume of a parallel pipette having sides A, B and C. Correct. Suppose I am representing I dot J cross K. Sorry, this is I dot J cross K. Or simply I dot J cross K. And this I dot J cross K is called the Levi-Civita symbol. Correct? It is denoted by the epsilon I J K. This is the vector world notation and this is the tensor world notation. In the realm of tensors, we write I dot J cross K as epsilon I J K. Now we will see what are the properties of these fellows. I dot J cross K. Whenever any two indices coincide, it will be 0, obviously. Suppose I is equal to j. Suppose I is equal to j. Means I can very well interchange cross and dot. So this becomes I cross I dot k. So obviously I cross I is 0. Suppose j is equal to k. So j cross j obviously 0. So in this symbol, whenever any two indices coincide, that vanishes. So epsilon ijk is equal to 0. Correct? There is a tensor notation. This is a vector notation. Correct? So what is Levi-Civita symbol? Levi-Civita symbol is nothing but the scalar triple product of 3 unity vectors. 3 unity vectors. Correct? So Levi-Civita symbol is the scalar triple product of 3 unity vectors. Another very interesting property is that suppose I is not equal to j is not equal to k. And obviously, and at the same time these are cyclic in nature. Obviously you can verify that this is always equal to 1. Correct? So all are having unity magnitude. Correct? Do that. So it is equal to 1. Suppose I, j, k are different but non-cyclic. But non-cyclic is obviously minus 1. Correct. Similarly, I can very well write this as epsilon I, j, k is equal to 0 provided any two coincides, which is equal to 1 when I, j, k are different and cyclic in nature. I goes to j, j goes to k goes to I goes to j. Correct? It is equal to 1. When they are non-cyclic, it is equal to minus 1. Now suppose I am collecting all epsilon I, j, k is possible in a 3-dimensional space. How many epsilon I, j, k can be collected? It's a very interesting question. In 3-dimensional space, I can be x, y, z. J can also be x, y, z. K can also be x, y, z. So totally in a 3-dimensional space, how many epsilon I, j, k can be collected? Altogether we can collect 27. Altogether we can collect 27. Go home and try this. Correct. Out of which we are having 3 numbers which are 1, 3 numbers which are minus 1. So totally 6 members will survive as 1 and minus 1. And the remaining 21 will be zeros. You check it up. I am not going into the details of this. It's a very simple thing. So collectively, epsilon I, j, k is an entity having 27 components called a tensor. Formerly, I introduced a tensor having 9 components. Now this fellow is having 27 components. Now I can very well correlate between the number of components. So look at this. We are dealing with the 3 dimension. Be very careful about that. Mij. Mij was having 9 components. We are dealing with the 3 dimension. Be very careful. And epsilon I, j, k having 27 components in 3 dimension. Now you can very well develop a very beautiful formula connecting dimensionality and the number of components. Correct? So these 3 can be written as 3 square 1, 2. This can be written as 3, 1, 2, 3. Now we developed a very famous formula in tensors. Correct? This is called a second rank tensor. When 2 indices are attached, it is called second rank. When 3 indices are attached, it is called third rank. When 4 indices are attached, it is called the fourth rank. I will come to that point later. Correct? So, a very simple formula can be deduced from this very simple analysis. Now, epsilon ijk can be easily found out by using this simple formula. Epsilon ijk is 1 by 2 I minus j into j minus k into k minus I. You can go home and verify this. This is another form of epsilon ijk. Correct? Or epsilon ijk can also be written as, or I already told you, I dot j cross k is equal to epsilon ijk. I told you the Levi-Civita symbol or a third rank tensor is nothing but the scalar triple product of 3 unit vectors. Now you can very well write what is I cross j. I cross k or j cross k. I think that is more better. J cross k. J cross k can be written as epsilon I j k into I cap. Correct. This is the vector notation and this is the tensor notation. On the left hand side, this is the vector notation. Correct? J cross k is obviously a vector. Epsilon I j k into I cap. Where does it come from? It's a very simple thing. Correct? Look at this carefully. Suppose I take dot with I. So I dot j cross k, epsilon I j k is a number, then I dot I dot I, and I dot I is obviously 1. So this is our formal definition. Epsilon I j k is equal to I dot j cross k. Correct? In order to memorize this, it's a very simple thing. Look at this. On the left hand side, you have j and k. Here I, j, k and I. And I is obviously dummy. Dummy means sum over. You perform that sum, ultimately I will vanish. And what is remaining? K and j. And this is what is called as tensorial checking in tensor analysis. Just like dimensional checking. Correct. So once again, let me repeat that. On the left hand side, you can see 2 letters j and k. Correct? On the right hand side also, you must have j and k. Correct? So, but you can see an I here. But here I is dummy. Dummy means sum over I. Sum over I means you perform the sum. When you perform the sum, the ultimate result containing no I. What is remaining? J and k. Here also j and k. So it is called the tensorial checking. So you should learn how to go from vector language to tensor language, which is more compact and simple. Tensor language is more compact and simple. Correct. For example, j cross k is epsilon I j k. Correct. Similarly, I can write I cross j. It's a vector language, meaning everybody knows. But I have to write in terms of tensor language. In tensor language, I write epsilon I j k, epsilon I j k into k cap. Obviously. into k cap. Look at, let me check once again tensorially. On the left hand side I have I and j. On the right hand side we must have I and j for tiling the left hand side and the right hand side. So look at this. Here k is dummy. There is a hidden sum. When we perform the sum, ultimate result containing no k. So only I and j. So this is a transformation. So whenever cross product in vector comes, in the tensor notation, there is an inevitable member epsilon I j k. Remember that. Otherwise you can go further in tensors. This is language transformation. I cross j is equal to epsilon I j k k. Let me quote an example for this. Suppose I have two vectors A and B. I want to find out the ith component of A cross B. Ith component of A cross B. I already told you, whenever cross product comes in the tensor language, Levi-Zeta symbol will come into play. That is A cross B. Automatically Levi-Zeta symbol will come into play. A can be written as some AI. Instead of B I can write BJ. Instead of cross I can write epsilon I j k. Or let me do it in a different way. I have two vectors A and B. I want to find out the ith component of A cross B. To find out the ith component of A cross B, what do we do is, which is equal to I dot A cross B. Ith component of A cross means I dot A cross B. Obviously, everybody knows. This can be rewritten as I dot. Instead of vector A, tensor notation is Aj into J. Cross. In tensor notation, B is Bk k. Aj and Bk are numbers. So Aj Bk. The remaining is I dot j cross k. I dot j cross k is epsilon I j k. So epsilon I j k. This is the result. So A cross B, ith component can be written as epsilon I j k A j Bk. Again checking, tensorial checking. On the left hand side, we are seeking the ith component, only ith component. So it should be the ith component. Look at this. Here j is dummy. So there is a hidden j here. Summation over j. Summation over j means you perform the summation, j will disappear finally. So j disappeared. This is dummy k. So this is a hidden sum over k. Perform that sum. So finally k will disappear. So j disappears, k disappears. What is remaining? Only I. Here also I. This is what is called as tensorial checking. So any cross product can be easily transformed into tensor notation. That is A cross B can be written as epsilon I j k A j B k. You need not write down this is the ith component, because looking at this you can very well see that it is ith component, because summing over j will disappear, summing over k will disappear, only I remains. So it is obviously the ith component. Correct? Suppose I want to write down angular momentum in terms of tensors. Angular momentum L in terms of tensors. Angular momentum in terms of tensors. It's a very simple thing. Wherever cross comes, epsilon ijk will come into play. So epsilon ijk R. Instead of A, I have H. So Xj, R has three components, X, Y, Z, or in our language, X1, X2, X3. That is Xj. P has three components, Pk. So this is a form of transforming a vector language to a tensor language. It is epsilon ijk xj pk. Summing over j will disappear, summing over k will disappear, ultimately I remains. After setting up the definition of tensors and the tools required to learn tensors, we will continue this topic in the next session. Bye.